Morning. Late. All right, we've only got 2.5 weeks left, but I don't know if you noticed there was a big jump in COVID cases on campus on Friday. So they jumped from 17 on Wednesday to 37, I think, on Friday. So, which I figured would be about, I figured if we got to 50, that we'd be going online again. So I wouldn't be surprised if sometime this week that we don't go online then for the rest of the semester, but crossing my fingers that we don't. If we do, I'll send you stuff from, I still will have class synchronously online. I don't know, maybe we can find a better time than at 8 o'clock in the morning, but I don't know if everyone's schedule will permit that, probably not. We are close to the end. We've got actually 2 more chapters to cover. So chapter 8 is actually on time varying fields. And this table kind of illustrates the additional terms that are present. And so these are Maxwell's equations. There are four equations that can be given. Typically, they're stated if you just look up Maxwell's equations, these are the four that you'll find. These are in the point form, the most general form that includes time variation in the magnetic and electric fields. If there is no time variation, these partial derivatives with respect to time disappear. So if the B field is not time varying, for example, if you have a steady current, if the D field is not time varying, if you've got static charges, then those Maxwell's equations reduce to this form, which is what we've built up to at this point in the semester. And then above that, you'll see the integral form. But one of the interesting things about about time variation in the static case, the presence of charge can create a D field. As a matter of fact, that's the only way we've seen at this point to actually create a D field, or to create an H field and the corresponding B field, since they differ by a constant. You have to have a current present or a current density. But now with time variation, you can actually have an electric field created by a time varying B field. And then that time varying electric field, of course, is a time varying D field, which can create a time varying H field, which again is a D field. So it's possible with time variation that changing, and they're coupled, a changing B field will create a changing E field, which in turn creates a changing B field. And that becomes wave propagation, actually. So, but, and that's the topic of the next chapter. But what I want to talk about today is electromagnetic induction. And so this leads to, I'm going to get a better marker here. This leads to transformers and also generators, both of which we'll talk about briefly today, and then in more detail next time. Okay. So, but the idea is a time varying, well, I'll put it down here, a time varying magnetic field can induce or create a voltage in a conductor. Okay, and so I'm going to try and draw my coil here with just a few windings, and then try and draw it in such a way that the windings are obvious. So this shaded area is the back side. And then in the past, I've hooked up a current source when we were talking about the inductance of the coil. But now I'm actually going to hook up a load and talk about the voltage produced across that load. And what I'm going to introduce now is a magnet, north and south poles. And it creates the magnet has a B field I'm calling B impressed. IMP is the subscript there. So the magnet creates an impressed B field. I'll be impressed. Going to be careful because we'll have, we'll be dealing with two B fields here, magnetic fields, the field created by the magnet, and then there'll be another B field created by the coil if current is flowing in the coil. Now, if the magnet, so if you set this up experimentally, what you find is that if the magnet is not moving, there's no voltage across the load, there'd be no current in the coil. So if the magnet is moving toward or away from the coil, there is an induced voltage. Now, there will also be, because I've got a resistor here, there will also be a current. So sometimes they'll say in this experiment you get an induced current. But there's only current if I've got a resistor across that connection and allowing current to flow. There is, so more properly, it's an induced voltage. I'll have a voltage there whether or not current is flowing in the coil. I'll have current only if there is a load across the gap, across the connection. But if there is a resistance that's shown, current flows in a direction so that the induced field, so if there's current in the coil, that would create a B field in the coil itself that opposes changes, the underlying changes here. It opposes changes in the impressed field. It doesn't oppose the field itself. In some cases, it will be aligned in the same direction as the field. In other cases, it will be opposed to the field, but it always opposes changes in the impressed field. This is called Lenz's law. It's not actually a qualitative, and there's no formula. Or it's not a quantitative, there's no formula, it's a qualitative statement, really. It allows you to find the polarity of the voltage, okay, but it doesn't actually tell you what voltage will be created. So here's an experiment. This is from a figure in the text, but I didn't want to take the time to draw it. Now, when you're looking at these, so this is a very simple transformer. Okay, two coils around, ferromagnetic magnetic material, just to increase the mu. So several things are important here. The primary side of the transformer is where the source is connected. So that's the left-hand coil here. And we've just got an open voltmeter across the secondary coil. But a lot of things are important here. One is the direction of current in the primary coil. The other is the direction of winding is important because you have to be able to determine the directions of the B field. So in this particular case, notice current would be flowing in this direction when I first close the switch, okay, in the primary. So notice the plus terminal, so this is our standard current direction. So if you'll notice, because of the way the primary coil is wound, according to the right-hand rule here, this would be the direction of the B field, the impressed B field. And now, when we first close the switch, we go from no B field to, eventually this will become a constant current, and then we'll have the current associated with, or the field associated with that constant current. It'll no longer be changing because I've got a DC source. But when I first close the switch and I go from a 0 field to whatever the final value is, my B field is increasing. It's increasing in the phi direction if I have Z coming out of the board and my coil and my transformer in the XY plane. What that means is, because it's increasing, the induced field would be in that direction to oppose the increase. In order to get a B field in that direction, I'd have to have current flowing in the coil like this, again from the right-hand rule. So current coming out of the bottom here. Now, in order to determine the polarity, you want to think about your coil here as a voltage source, as a generator. So current comes out of our positive terminal of a generator or a voltage supply, right? So in this case, we would see a positive voltage. Now notice here, if this is an ideal voltmeter, there may not actually be any current flow. There may not be actually, and if there's no current, there actually wouldn't be an induced B field. So this is all just kind of a trick to help me determine the voltage polarity. Now, if there were an actual load there would be current flow and there would be a B field in that direction, an induced B field. Now, this induced B field only exists while the impressed field is changing. Okay. So once the current on the primary side settles down, we wouldn't have an induced B field, we wouldn't have a secondary voltage. Transformers only work when you've got time varying voltages on your primary. You can't transform a DC voltage. And that's primarily the reason, we use AC power. I guess that was the argument between Tesla and Edison. Edison wanted to use DC power, but the problem with DC is you can't transform it. So with AC, like our sinusoidal voltage, we can transform that up to very high voltages, which we can transmit long distances at low currents, because power is voltage times current. And if we have to transmit power a long distance over a conductor, we want to do that using very little current to minimize the I²R loss in the conductor. Okay. You get power loss in the conductor, it's a function of the amount of current, and that's wasted power. That's just lost as heat in your transmission lines. So power transmission, we want to transmit it at really large voltages, hundreds of thousands of volts. Now, that would be very dangerous to have that voltage coming into the house. So they have another transformer near the house where they step it down to a much safer 120 volt level. And then the currents consequently are much larger coming in the house, but that's over a shorter distance. So that's kind of why we use AC powers, because transformers exist and transformers only work for AC voltages. Okay, so this is what happens when the switch closes. So what you'll see is on this voltmeter, the needle will swing to the right, and then it'll come back to 0. Okay, even as our battery stays connected. We'd have to have a changing voltage source over there, you know, a sinusoidal source, in which case we'd see the voltage here vary sinusoidally as well, swing back and forth. Now, when we open the switch, our impressed B field is still going to be in the same direction, but now it's going to be a decaying B field. It would be going from whatever its steady state value is back to 0 as we, you know, after I open the switch. The induced B field opposes changes in the impressed field. So since this impressed field is now decaying, that means my induced B field would aid the decaying B field, which means in this case, the current, you know, my coils here, my field lines are inside my coil, so my current has to be in this direction, okay, which means the current now has to be in this direction, means it has to be coming out of the top of the coil. So view that as a voltage source here. That means this is plus, this is minus, which means now as I hook up my voltmeter, it would swing to the left. Okay. And I'd see a negative voltage on my voltmeter. So as I close the switch, I'll see the voltmeter swing to the right. And then it'll go back to 0. I open up the switch, I'll see my voltmeter swing, needle swing to the left, indicating a negative voltage, a negative induced voltage, and then it'll go back to 0. And then I could just repeat that. Now it's really important that you understand this, because this is a sign convention, because the next step is to actually make a quantitative statement about this relationship. That brings us to Faraday's law. But understanding Lenz's law and these, and in particular the polarity of the voltage here, will go a long way in helping you understand Faraday's law. Now, change the polarity of my voltage source, everything changes. Change the winding direction on either coil. You know, we have to go through the analysis. Change the winding direction here, so it comes over the top now. Then my impressed field would actually be going the other way with the same polarity voltage source, right? And so everything would be different. And in that case, I get a negative voltage when I close the switch without changing the secondary coil. So, you know, all of this is important in determining the polarity of the secondary voltage. So understanding the right-hand rule is critical. Okay, so let's look at Faraday's law. Faraday's law will actually allow us to calculate the voltage across the secondary. So we're going to start pretty simply with just a single loop conductor, kind of like how we first looked at a single loop coil, kind of how we first looked at inductors, but I'm going to leave a little gap in the coil. I'm going to put a resistor across the gap, and I'm going to have, again, an impressed B field that's somehow externally generated. Might be an electromagnet, might be a permanent magnet. Now, I'm going to pick a polarity for that voltage, and I'll have more to say about that in just a bit. Actually, the polarity choice here is arbitrary. And so you pick one and then everything else follows from that. But now once I pick that polarity, it's important to pick a current direction that's consistent with that polarity. Again, you have to think of the loop as a voltage source. If I think of the loop as a load with a plus voltage here and a minus voltage here, we'd expect the current to be flowing clockwise through the loop, right? If I view the loop as a load, you have to view it as a generator. The resistor is my load. So current would be flowing counterclockwise through the resistor, to the right through the resistor, and that determines my current direction, my reference current direction in my coil. And that's tied to the polarity of this voltage. The other thing that we'll see, we need to evaluate a surface integral here as part of Faraday's law. And so I need a normal to the surface enclosed by this loop. I say the loop is bounded by a contour, and my contour integration is in the same direction as my current. Now I apply a right-hand rule, which means my normal to my surface would be in that direction. So if you get this wrong, you're going to be off by a minus sign. So there's a series of polarity of the voltage, determines everything though. If I'd actually reverse the polarity of the voltage, my current would be going in the opposite direction. My contour would be in the opposite direction, and then my normal to my surface would be on the other side of the surface. But Faraday's law is that the induced voltage is the negative time derivative of the flux through the surface, where here's the equation capturing the flux, B dot BS, that's our standard equation for the flux. So Faraday's law tells us actually that it's the time varying flux through the loop that creates the voltage. You know, this kind of mental experiment we did over here with the magnet and the coil might lead you to believe it's actually the increasing intensity of the B field that leads, and that's part of it. If my B field intensity is changing, my flux will be increasing. But it also depends on the area of my coil. Now, here, you know, if the area of the coil is fixed, then it's tied directly to the changing B field. But there are problems where we can get a time varying area in my loop. And that's actually a generator principle if I'm changing my surface area. So both of them actually are important. And the negative sign here in the equation captures the fact that, let me see if I can get this right. So let's talk about a constant loop area. If my B field is increasing, so my flux is increasing, my current would have to be my B field would have to be opposing to that. So let's say my B field is Z directed. My induced B field would have to be negative Z direction, which would correspond to a current flowing in the opposite direction, which would produce a negative voltage. Okay. So if the flux is increasing, VT would be negative. That's what the minus sign tells me. If the B field is decreasing, then my induced B field would be in the same direction to oppose the decrease. So the B field would be in the same direction as the impressed B field, and so the current would be in the direction shown, and then VT would be positive. But if if the flux is decreasing, then its time derivative is negative, and the negative of the negative gives me the positive voltage. Okay, so here's the, I'm going to write out the sign convention. So pick a polarity for ET. Can't go wrong there. Okay, it doesn't matter what you pick. I just picked plus on the left there and negative on the right. And then the loop contour is directed around the loop, not across the gap, from minus to positive. So again, once I pick this, that determines my contour direction. Plus minus, again, it's from the minus around the loop to the plus. So my contour would be in the counterclockwise direction in this particular loop. Now, I say it in terms of the terminal voltage instead of the current, because if I don't have a resistor there, there's not going to be any current. But if it helps to think of in terms of, well, what direction would the current be? You know, you can certainly use that if you want to pretend that there's a resistor there even when there's not. But remember, this thing, the loop is like a generator. And the current comes out of the positive terminal of your generator. And then the direction of N is determined by right-hand rule relative to C. And again, if we have a resistor across the loop, the current would be flowing in the same direction as my path contour. With N identical loops, Faraday's law generalizes to minus N partial derivative of T with respect to the flux. Okay, we'll work through an example problem here from the text in just 1 second, but first I want to list a couple of different ways we can generate time-varying flux. In several ways. One is using a fixed loop or constant surface area for my loop with a time varying be impressed. And so typically in physics, and it's common when you're talking about electromagnetics, instead of using the term voltage, we'll call it an electromotive force or an EMF as the term, but it's the same as voltage. But with the example we looked at here, this is a simple transformer. So this is a transformer EMF that's generated. And this is the basic principle of all transformers. And so if to get the, and it doesn't say that there, but to get the time varying compressed V field, I need a time varying primary voltage source. And DC won't work unless I got somebody manually operating a switch there, right? Or mechanically operating a switch. Actually, that's kind of how these DC to DC converters work. Actually, you get electronic switching, opening and closing to transform a DC voltage to another level, but it's based on this transformer operation and essentially an electronically opening and closing switch. But normally we use it to transform DC or AC voltages. The other way, well, another way, is with a fixed B with a time varying surface. And that seems a little odd, how can I get a time varying coil surface? And it's not really often that the cross-sectional area is changing. It's that it's the dot product here. Notice that my flux is a dot product with a B field and the normal to my surface. So I can change that by rotating the surface, changing the direction of N. If it's perpendicular to the B field, then the flux is 0, right? So I have it here kind of, my B field's like this, and my loop's like this, I'm capturing maximum flux. But if I just rotate this thing, spin it here at 90 degrees, then it's capturing 0 flux. So it's really not, I'm not changing the cross-sectional area so much there as by changing the direction of my surface, the normal. And that's the basic principle actually of a generator. We have something mechanically turning loops through a magnetic field, and that will generate an EMF. This is called motional EMF, and it's the basic principle of generators. And in the more general case, you have a time varying B field with a time varying surface. So we'll work through one problem from the book. And this is actually the more general case. So we'll talk a lot more about generators in particular. Transformers are pretty simple. Okay, and you work some transformer problems in the homework. Generators are a little bit more difficult to analyze. This problem talks about actually a general case where we've got a time varying B field and a time varying loop size. So the loop is in the XY plane. Tell you it's got a gap in it, so Z is coming out of the board. And they tell us the B field is Z directed, but it's increasing linearly with time. That in itself would create a terminal voltage across that gap. Now, here in the problem, they specifically state that the plus terminal is plus phi directed from the minus terminal. So they give us the polarity in the problem statement. and that doesn't really matter. You know, if you had chosen the opposite polarity, you would just get the negative result, right? A negative voltage just means that the polarity is, it's not wrong. It's just if you swap your reference, then it would be a positive value, which means our contour would be in this direction, right? From a minus round to the plus, which means that my surface is actually coming out of the board. Is that what I had? Did I read this problem right? I think that's, I have to go back and look at the problem. I think that's, I think I did the polarity right. I don't remember that. I didn't bring the problem. Okay. And it said the radius of the loop is A, but A is constantly increasing. How they would do that, I'm not sure. Okay. But it's a theoretical problem. So our loop is getting bigger and bigger. A is the radial distance, and V is just the constant velocity. So the radius is increasing with constant velocity. Okay. At any instant in time, our flux is going to be the integral of B over the surface area. So both of these are actually changing. What would be the direction of ds, though, with this convention that I've got here? Says determine, so it's going to be either plus z directed or minus z directed. What do you say, plus z? You apply the right-hand rule. So, okay, so, but you got to use your contour. So, put your thumb in the direction of the contour. Your fingers then will, inside the loop, will point in the direction of this normal. Or curl your fingers in the direction of the loop, and your thumb will point in the direction of the normal. So it's into the board, but my z-axis is coming out of the board. So ds here is actually negative z directed. And it would be rho d phi d rho. So, and that all comes from this choice of polarity, actually. If I had chosen the other polarity for the voltage, my surface would have been z directed. So if I'd gone, you know, plus minus, and I think that's what I had over there, right? Yeah, plus minus, then it would have been out of the board. So, but doing this, I'm going to pick up this minus sign. I'll have E0, 1 plus KT, then rho d phi d rho. My integral here is from 0 to 2 pi and 0 to A. So this actually doesn't depend on any of the dimensions, so I can pull it out. It's actually, let me write it like this. It's actually minus my B field times my time varying loop area. I pick up time variation in my loop. I because A here is varying, the radius is varying. So this becomes minus E0 1 plus KT times integrate rho, I'll get 1/2 rho squared. And so the 1/2 will get rid of the pi. This becomes just pi A squared, right, which is the area of the loop. But one plus KT. But A is V squared T squared. So I was trying to be a little careful here about what portion is due to the changing B field. What portion of the flux is due to the changing B field? That's this portion. This would be the part that leads to transformer EMF. This portion would lead to motional EMF, because, and you don't, there's no need, well, in another part of the problem here, they ask you to identify those two parts and at what time they're equal in magnitude. So for that part, you would need to keep them separate. But for what we're doing right now, just trying to find the voltage, I really don't need to. But the gap, I think he has it here, and it's the negative time derivative. So that would be AT dB dt plus BT dA dt. And really it's this part that's the transformer EMF. And this part that's the motional. I wrote them over there, but those are actually fluxes. At this point, these are the terms that actually lead to voltages. The transformer is due to the time varying flux, and then any change in area produces the motional EMF. And you don't really have to do it this way. What we have. So I'm going to write down this equation again. Minus B0, 1 plus KT, and then pi B squared T squared. I guess I'll go ahead and do it this way. So my gap voltage it would be pi B squared T squared. So I'm just using my product rule. You could multiply this out, but the derivative of this term times this. So the derivative, and then get the negative. So this is going to be just KB0 for the derivative of this. And then plus, again, my negative goes away because this minus sign. It would be B0, 1 plus KT. And the derivative of this would be 2 pi V squared T. I can simplify this a little bit. There's some common terms. I've got pi squared, V squared. I've got B0 that's common. And pi V squared, B0. And a T that's common. So I can have V squared T. And then here I'm left with a KT. Here I'll be left with just a 2 and then a 2 KT. So if I did all that right. And so finally my gap voltage would be 2 plus 3 KT. In the final form, it's a little bit difficult to identify which is due to the motional EMF and which is due to the transformer EMF. Actually, if I set but I think that's the final result. And that's the most general case where you have both a changing B field and a changing surface area. And generally, it's not the surface area changing so much as the direction of my surface. And because of that dot product, I get a time varying flux in that case. Okay. That's it for today. So